So Mark, if I can ask you just to step over. You could just tell us a little bit about yourself and what you're going to talk about today.
Okay, Mark Maylin from a small company called 3Sci, a bunch of entrepreneurs who set up a business a few years ago. Mostly from a defence background, but kicked off in oil and gas about 20 years back. Today I'm going to talk about how to get rid of steel through a process of accelerated corrosion.
Excellent, thank you. And Roger, can you tell us why this is of interest to us here at the OGTC and to the industry at large?
So this is a really interesting project. This is the result of our one of our first project through the Decommissioning Solutions Centre. And when you look at the expenditure that we're going to have in decommissioning over the next 10 years or so, and if you actually just look at the structures that we have in the marine environment, with nearly 900,000 tonnes of jacket and subsea infrastructure there, and a total bill of somewhere in the region of £3 billion for that. And this could be a technology that helps us to reduce that cost for it.
Excellent, thanks very much. Okay, and with no further ado, I'll hand over to Mark, and your 20 minutes start now.
Okay, thank you. Well, thank you all very much for coming along today. Very nice to see you all. Making steel disappear by accelerated corrosion. This was a theme which has been around with myself and my colleagues for quite some years now. Not least of all because we had the need with certain defence applications to cut through bits of steel in a relatively silent and stealthy way. So when the call went up not long ago, how might we be able to get rid of steel subsea, we took the view that we could go back and look at this electrochemical process one more time and look at how we could actually apply this to getting rid of oil and gas steels. Just very briefly, a quick introduction to 3Sci and the team. There's our CEO, Mike Hinton, A.D. Bowles, our technical director, and myself. We're the three founders of the business. We thought about some quite imaginative names for the company originally, but being quite sort of scientific and mathematical, we looked at each other one day and said, okay, well, we're three scientists, so we just going to call ourselves 3Sci. It's quite a good idea in a way, because only if 3M turn up at a conference that we not get popular. We're actually down on the south coast here. Those of you who see this presentation in a different form will be quite relieved now that we've actually got Wales on the map as well, and Cardiff. So we're actually down here in Portsmouth, Hartwick, in Pompey and Southampton. The team is comprised at the moment of 9 individuals with quite a lot of experience in developing new technologies and producing new products. Removing steel subsea. I imagine quite a few of you are familiar with the primary options. I'll just go through these very briefly for perhaps some of you who may not be. People often think about the use of explosives, mechanical or grinding, cutting methods using hydraulic or electric actuators. Often people think about using high-pressure water jets with abrasive, which do leave an awful lot of debris and unwanted contaminants in the marine environments. And of course, people often think about chemical ways of dissolving steel using very strong chemicals and acids. One of the problems, for example, with many of these approaches, but if you take, for example, the explosive technique, looking at the image at the bottom right-hand corner of the slides there, you can see how difficult it is to produce a clean cut where you don't get flaring. And so if you cut in a tubular and you've got a flaring of the pipe near where the cut was made, it's then possibly sometimes quite difficult to pull that pipe out of a very restricted region. So accelerated corrosion does offer some advantages in that it is quiet and, frankly, quite simple. What do I mean by simple? Well, here's one you can try at home. Do it in the back garden, please. But if, for example, you take a car battery and you take the positive red wire output of that battery and you connect it to a piece of steel, and some of that steel might, for example, be masked off with a bit of duct tape or paint or whatever. And then if you take the negative part of the battery, just a DC power supply, and you attach that to an inert anode, a piece of copper dangling in the seawater in close proximity to the steel. In a saltwater solution, the steel will then disappear like aspirin. So that's the essence of the technique. Just a simple DC electrical power supply delivering direct current into the steel in a conducting saline solution in this case, with steel just very gradually dissolving from that steel surface in the proximity, in the location close to the, in this case, copper cathode. That's the essence of the technique. And here's some examples of some work we've been doing, some experimental results. In this case here, we have a piece of scaffolding, so that's about 2.5 inches diameter, probably about 1/4 of an inch, 6mm wall thickness. And by arranging a copper cathode as a ring placed around that scaffolding, the scaffolding disappeared probably in less than an hour for a few tens, about 60 or 70 watts of power delivered to that circuit. Sorry, did I accidentally do something? I made it all disappear. Maybe I accidentally touched the black bit, okay. Seems to be a 40 at mine, making things disappear. So the second example here, excuse the blurry image, unfortunately it was the only one I had, is where we've actually drilled a hole in the steel pipe. In this particular example, the cathode was arranged pretty much as a singular point, a rod, sitting in very close proximity to where the hole eventually emerged. We did a little bit of masking off of the steel around the outside of the hole, but again, it gives you an example of what one can achieve by this accelerated corrosion electrochemical technique. And then over in the far right-hand corner there, an example of taking a small sheet of steel, which again, you can see the corrosion, the pitting of the surface when a cathode is placed in close proximity to that steel in a saline solution with the battery pack attached to it. So again, some further examples of work we've been conducting recently. Relatively small tanks of water, tubes about that big, about 1/2 meter or a meter long, and typically 10 or 20 centimeters diameter. It's a bit unfortunate, this one, do excuse me, we've actually got the wires the wrong way around in terms of the colour. That should be the red wire pumping positive current into the steel. And this should be the black wire delivering current back to the negative of the battery pack, excuse this image. And then the cathode as an angular ring placed around the steel. And what this results in is, this is an image of the tank of that solution an hour or so after the process has been progressing. And you can see the corrosion products forming quite nicely here. You can see sort of like a reddish brown corrosion product on the surface of the liquid, which is probably a high percentage of hematite, Fe2O3. And if you look very closely, you can see the rather more darkened colours at the bottom of the tank, which does eventually turn out to be a strongly magnetic phase of Fe3O4. So it's typical rust products that transform into the sorts of rusts we find on our badly protected cars. And again, just to give you some idea of the additional work we've been doing recently, here's a pipe, a steel pipe again, sitting in a rather larger tank, with a cathode, copper cathode in the form of a mesh placed in close proximity to the steel. We like to choose meshes for the cathode in some of the work we've been doing so far, for a reason which I'll explain to you in a moment, associated with the gas which is generated in the accelerated corrosion process. And a copper mesh is a nice way of getting the area of the copper quite high, and in particular dealing with the gases which are created. And the image down in the bottom right-hand corner there gives you sort of like a different view on this image here, where you can see what the standoff is between the cathode and the steel pipe. And then what we have here is a couple of videos where I show what's going on when the electrical currents are flowing. So in this particular example, you can see in the background the copper pipe, but in the foreground you can see hydrogen gas being generated at the cathode in quite large quantities. When you look at the chemistry, which I've very loosely outlined in the writing at the bottom of the image here, you can see that hydrogen is a natural product of this accelerated corrosion process. And as we move forward and consider how we deploy this technology to larger and larger scales, capturing that hydrogen as a useful energy source could be very helpful to us. In the close confines of a relatively small bucket, you can see the corrosion products again forming during the electrochemical attack experiments. Originally, this solution looks a bit green. Our view at the moment is it's probably predominantly iron hydroxide being formed, which we think then very quickly transforms into the iron oxides, into Fe2O3 and Fe3O4. We've got a little bit further to go in terms of getting to grips with the precise transformation rates of the corrosion products which are being created by this electrochemical process. And just to give another example of what happens with this particular technology, we start off with a piece of steel there, again, probably about 2.5 inches thick, and if I recall correctly, that was about 6 or 7 millimeters wall thickness. And after about 20 hours at 20 amps within a day, we ended up taking that structure down to this structure in a relatively small containment tank. This was probably about 900 grams or a kilogram, and this is down at 300 or 400 grams. So it gives you some idea of the corrosion rates which we achieve. But if we let that go on for another day, it would have all disappeared. So energy requirements are important, and we're gradually working our way through an understanding of what sort of electrical energies, what sorts of powers do we need to be able to get rid of steel by this technique. Perhaps a good starting point to remembering this is you get rid of 1 gram of steel for 1 amp delivered to the steel and delivered through that electrical circuit when that amp has been delivered for about an hour. And that comes directly out of the electrochemistry, directly out of the electrochemical equations. It's approximately correct. If I remember correctly, I think it's about 1.1 grams per ampere hour. So just by simple extrapolation, you can see that a kilowatt of power, going with the view that we are reasonably confident we can keep the resistance of the circuit at significantly less than 1 ohm, will give you about 1 kilogram an hour. And if we linearly extrapolate that, thinking very ambitiously as to what we may eventually be able to achieve with this technology, quite simply, a megawatt would dissolve 8,700 tons per annum. So you can see immediately that from this very simple piece of electrochemistry, I don't think these are unrealistic expectations that we get through linear extrapolation. We could actually be dissolving quite significant quantities of steel by using relatively high powers. One of the issues which I raised earlier on is the available energy in the hydrogen gas. And we haven't looked yet at the possibility of how we collect the hydrogen gas. Clearly it's a question of just capturing it. When you look at the electrochemistry involved here, for every atom of iron which you're dissolving, you're producing an atom of hydrogen. So there are some significant quantities of hydrogen being produced that we should be able to capture and reuse as an energy source to contribute towards this process. So this estimation at the moment that we will be roughly in this ballpark of a kilowatt per kilogram per hour, that may even now be pessimistic. And with the use of the hydrogen, the efficient use of hydrogen, we may be able to get this down to hundreds of watts to achieve a kilogram per hour of dissolution of the steel structure. When you think about perhaps the typical masses, say, of a jacket, 20,000 tons, doing a few back of the envelope calculations, and immediately 20,000 tons would require 20,000 megawatt hours, 72,000 gigajoules, which I understand is a relatively small fraction of the amount of energy being used right now to take 20,000 tons back to shore and treat it and dismantle it and recycle it. And even if you use the diesel generator, you calculate immediately that the cost of getting rid of that steel would be approximately £400 a tonne, on an expectation that the diesel is costing £1 per litre. My best understanding at the moment is it's taking several thousand pounds per tonne, pounds of money per tonne, to take steel back to shore. Just a few examples of how we see tools being created and deployed. If, for example, you want an in-tubular cut, for example, this may be a piece of casing, we can see immediately how we can arrange the cathode to be located in a region where you're trying to settle the steel at one axial location, with electrical current being fed down to an anode. In this case, we're looking at a non-contact anode, where we're not making a very intimate direct contact from the anode to the steel. We know that this can work. It does consume more energy by this mechanism, and unfortunately it does favour the production of chlorine gas. So we're not sure at the moment just yet, we're not sure at the moment just yet as to whether or not we will actually pursue in much more detail the non-contact approach. Thinking about another way of deploying this technology, schematically, from a personal perspective, I've done a lot of work in inline pigging. So I'm naturally inclined to consider how one can actually deploy an accelerated corrosion tool inside a pipe in a manner which is very similar to how you would do with an inline inspection tool. One of the, from the earlier images, you'll remember there were corrosion products being created. Sometimes those corrosion products could get in the way of the electrical current flow in the circuit. So, for example, if we designed an inline pig where the cathode was sitting inside the pipe, with the cathode's copper mesh in reasonable proximity to the steel, we may need some additional circulation of the liquids in order to make sure that the corrosion products didn't actually get in the way and create an electrical barrier between the steel and the cathode. And then perhaps this most ambitious, not sure just yet if this is fanciful or whether or not we can get there with good engineering design. If, for example, we considered footings, the many, many thousands of tons of footings which one may consider attacking by one or two different techniques. Obviously, people are getting derogation for footings at the moment. But again, if we came along with a high power, electrical power, we then created the steel as individual anodes in the circuit. We then might consider a hydrogen capture hood to give ourselves another 50% more energy in this process. You can see immediately how we may be able to slowly but surely over many years or many decades eat away at footings. So that just about sums up my presentation. I'm keeping a careful eye on the clock to make sure I don't get pulled in. Next steps, to validate this technique at larger scale. Most of the work you've seen today has been done at the laboratory scale in relatively small tanks. To confirm the precise availabilities and approaches for delivering electrical power in the field, whether or not we use offshore turbines, whether or not we use power from land, whether or not we use diesel generators, to be very carefully considered moving forward. One of the issues which is there for us with many subsea steels is that they are coated. They'll be coated with concrete, coated with polymeric layers, bitumens, epoxies, and those coatings will actually form an electrical barrier which will not allow the electrical currents of this technique to flow from the steel surfaces. So we do need to work out how we're going to address removal or partial removal of those coatings in order to enable the electrical currents to flow. But moving forward and expecting that we should be able to find solutions to most of these challenges, the expectation then is we'll get into later this year, in 2019, scaling up for prototype devices which will take the sea trial. And obviously making sure as we go, we're on the right side of the environmental impacts. We understand what the environmental impacts of this technology will be. So, I'm trying to stop the clock at 007. Okay, I think I'm going to fail. So that's the end of my presentation. Thank you all very much for listening.
Thanks very much, Mark. Yeah. Okay, and now we're just going to go into the Q&A. So if you've got any questions for Mark, just wave us down and we'll get Lauren with the mic over to you so we can make sure we pick up your questions. So who's got the first question? Oh, we've got a rush. This gentleman here, we'll get to you next.
Hi Mark, I was just wondering what you propose to do with the anodes that we use to protect the jackets. I think they would need to be removed and then priority first.
Top level answer from an electrochemical viewpoint is that those anodes will actually disappear in the same way that steel does. So where you've got the intimate contact between, say, a zinc or an aluminium anode and steel, in all probability the zinc will preferentially disappear first because of where it is in the electrochemistry. And then once that particular zinc has gone in that very tight location, that very small space, then the steel around it will disappear as well.
And bonus question, with the diesel generator, where would you site that if you've just got a jacket and stuff?
Yeah, probably on a piece of steel standing, but not sure about that yet.
Yeah.
So we'll have to think of how we deploy and leave the diesel gen in place if that was the right way of delivering the power. Obviously, one would perhaps prefer to deliver this from a more environmentally friendly source. Thank you.
You're moving into the follow-up there, Roger?
All I was going to say was we've got a couple of options at the moment that came out of the open call for innovation for vessel-based type support for that, so that could be one of the ways to look at that. But what we'd really like is a partner from the operator community that might help us to move this on to the next level. So,
Always pitching this gentleman here and then we'll move to you next, John.
Hi Mark, thanks for that. When you're looking at the pipe, sort of erosion from the inside, have you done any work on what would happen if you had sort of like an oil coating or a wax coating that would mess the electrochemical up?
We haven't done any work specifically. One just has to consider, is that particular coating forming a very firm electrical barrier? Electrical current is very penetrative, and if there are any small micro holes, not the right word, but if there are any small opportunities for the electrical current to flow, then that current will flow. But if, for example, that wax was forming an impenetrable barrier to the electricity, then clearly we'd have to get rid of that wax first. But we haven't done any work in that space just yet, so I'm not sure what the impedance, or the electrical impedance of those oils or waxes would be.
Thank you. And John here.
Okay. So, is there any environmental concerns to releasing 20,000 tonnes of iron in there in a limited period of time? And
in the first instance, we'd have to be extremely careful as to how the corrosion products were released, what rate they were released at. And so one of the factors going forward has to be, one of the bits of thinking going forward, has to be what's an acceptable rate. We end up with corrosion product, which as far as I understand at the moment is not going to be significantly different from any other corrosion products we end up with. Lots of rust. And if, for example, I'm not trying to dismiss the issue here, we do have to think very carefully about this, but just to give, say, a little bit of context here, my understanding at the moment is that there are many millions of tons of iron being naturally deposited into the oceans on an annual basis. From volcanoes, from other natural environmental sources. So we have to weigh what is, say, the contribution of the additional iron going into the ocean as compared to what is the natural background anyway. And there's a lot more work to do in that space at the moment.
it's more about the rate. I mean, there's natural oil seepages all the time in the North Sea, but the public screams that we have an oil leak.
Yes, of course.
So it's not a matter about, you know, and again, I guess the other thing, my other question is the cathode. How for a 20,000 ton jacket, how big would the cathode have to be?
I'm envisaging at the moment a series of much smaller cathodes. So I'm not imagining a cathode which would envelop the whole jacket structure. I'm imagining much smaller cathodes placed around the structure. In that particular case, it's probably in a situation where you're working from the top going downwards, not reasonable to avoid any accidental toppling if one part of the structure lower down receives more accelerated corrosion than parts of the structure higher up. So we'd be looking at cathodes which would be wrapped around individual components and legs and bracing structures of the jacket, and then of course going back with electrical cables to their electrical power supplies. So I'm not imagining something the size of a football pitch or more. That's one discrete element. Okay. Thank you.
Thank you. Next question, please. Gentleman here at the front.
A follow-up to that question. In terms of percentages of mass that you're losing, what sort of percentage of the mass ends up on the seafloor? What sort of percentage of that mass is drifting off on top of the sea?
I'm not sure about the answer to that question at the moment. Somewhere in the... can I have the flicker again?
Sure.
Thank you. It is an appreciable percentage, there's no doubt about that. If I go, oops, wrong way, I'll go backwards, that's it. I've avoided trying to write the chemical equations incredibly precisely because there are secondary and tertiary reactions which occur. So the rates of production of these compounds, of these byproducts, are quite difficult to assess at the moment, at any particular moment. But when you look, say, at Fe2O3 and Fe3O4, I think at the moment it's quite reasonable to assume that the total mass of those being produced will be a reasonably large fraction, or a reasonably large percentage of the total mass of the original structure. 50%, 60%, that sort of ballpark. So you could imagine that you're breaking down into minute corrosion products. Thousands of tons of steel actually got several hundred tons of rust, which is then being dispersed and broken down.
Disappears probably not quite the word for the process that's happening. But one other question would be talking about corrosion products. What about potential byproducts or any biological life that might be living on there? Is there any consideration being put into anything less desirable coming off in these reactions?
I think what you're looking at there is that those are the first order products coming out. Iron hydroxides, which we believe are then moving on to typical rust oxides. Ferrous chloride, and obviously sodium hydroxide. I don't think there's anything else immediately coming out of it, which is beyond what I've written there. If you were clumsy with the way in which you run the circuit, you could actually produce some chlorine as well. But obviously we need to make sure we don't do that in the electrical design. Did that answer your question, or did I miss the point slightly?
It's a good answer. I don't quite answer the question, but it's good enough for me.
We'll catch you up for those as well. Sorry, I didn't
Thank you. Next question, please.
When you've done your tests, how much extrusion is there on the corrosion past the cathode? Does the cathode have to be like dead level? If you stop at a line with your cathode, does the corrosion stop there, or does it sort of creep over?
It creeps over. It's not incredibly precise. For example, again, I apologise for the blurriness of this image, but in this, you can see here the value of duct tape, and this is a piece of scaffolding with duct tape wrapped around it to isolate about, as far as I remember, a centimetre or so of scaffolding axial length. In this particular example, I'm not quite sure we did as good a job as we would like to have done with the duct tape. And so the point cathode, which was in very close proximity to where the hole was, you can see was clearly attacking the steel in close proximity to the main target point. So there is some sort of distribution. of current. It's probably some sort of exponential law or something like that in the close proximity to the cathode, where the steel is gathered on the basis of proximity.
Thank you. Next question. Anyone? No? Okay, in that case, I think if we're done with our Q&A, I'll just pop over to Roger if you've got any thanks or any thoughts on what you've heard today.
No, just a vote of thanks for Mark. I mean, this is one of the first projects that we've kicked off in the Solution Centre, so it's great to see the first outputs from that. And I think we're interested now in how we move this forward and where we could take it next for a bigger trial, whether that's something we can do with the universities, but I'm interested in talking to any of the operators or supply chain companies here that would be interested in helping us to move this on to the next phase. But no, thanks very much, Mark. It's good.